existing as the separate form. 97 of them are still going to be together. Okay? Now, if you have 100 couples that went as just friends, basically all 100 of them, as soon as they get to the prom, are going to be off by themselves. Okay? They are not going to be together. But if you have a situation where you have a weak acid, and here's the dichotomy. Weak acids have strong conjugate bases. And that's what allows that to happen. So you separate it, but it goes, man, oh, I feel so alone. And it's not liking it. So it goes back to the molecular form. So this is the dichotomy. The stronger the acid, the weaker the conjugate base. The weaker the acid, the stronger the conjugate base. Okay? So if you're comparing Ka values, you have to look at how this plays out mathematically. So mathematically, when you look at, again, how you calculate Ka, this is why I said AP Chemistry is a math class, but I get to play with cool toys and blow stuff up. So this is a math class. The only way you can make a small Ka is what? Divide by a big number, and you have a small number up on top. Okay? So here's, and oh yeah, so things not to do with Burkamp. Now this will make sense to you. Number one says Ka times Kb is water. We'll get into that later. Okay? Number two, ask for the Ka of a strong acid. Why would that annoy me? It doesn't exist. Why? It's a really, really big number, and you're dividing by 0. Mathematically, it doesn't make any sense. Okay? So, if you look at sulfuric acid, anybody happen to know the formula for sulfuric acid?
H2SO4.
Beautiful, H2SO4. Okay? So H2SO4 is what's known as a diprotic acid, okay? Which means it has 2 protons. That's why it's diprotic, okay? HCl is monoprotic because it only has 1. Phosphoric acid, which is H334, that's triprotic, okay? Most acids are monoprotic. So what this means is that this ionizes in stages. You could pull off 1, and then you have HSO4 1 minus, okay? So if you look in your book and you try and find the Ka value of sulfuric acid, and that Ka would be the hydronium ion times the concentration of your HSO4 minus divided by the concentration of your H2SO4 at equilibrium. So at equilibrium, how much of this original H2SO4 exists? None of it. You're dividing by 0, or a really, really, really small number. So the Ka value is undefined, or a really, really big number. So if you look on that chart and you find sulfuric acid, the first Ka1 value just says, hey, they employed, hey, doorknob, it's a strong acid. It literally just, it's very much employed that your doorknob, don't ask, it's a big number. That's why it's not listed, okay? But the second one, and you can make this analogy with parents, okay? So here's your parents, your SO4, that's the parental group, okay? And they have 2 kids, Timmy and Tommy. So Timmy's the annoying one. So this is Timmy. So basically the parent, we go to the zoo, Timmy goes over by the lion cage, Timmy's no more. Parents don't care, Timmy's annoying, but they still have Tommy left over. Okay, so we have completely ionized Timmy, and we don't feel bad about that at all. Okay, it's Timmy. You'll hear me talk a lot about Timmy. Timmy's annoying as all get out. Timmy is now gone. But now they're kind of feeling bad. It's like, well, we do have 1 kid left. Maybe we should hold on to the 1, because that's going to be awkward if we go back home, like run into grandma and grandpa. Where are the twins? We were at the zoo. Lion cage. So now if you look at the second one, so this is Tommy. So now this can form H plus and SO4 2 minus. Now, you'll notice there is a Ka value listed for this one. So if you go to the Ka2 column for HSO4, there's a number. So now, this is why this is Ka2, because it's the second proton. So this would be the hydroniums times your SO4 2 minus gives HSO4. So sulfuric acid itself is a strong acid. It completely ionizes. This is Timmy being near the lion cage. Parents don't care, Timmy don't care. This is Tommy. Kind of like Tommy. We don't want to lose close kids. So there's going to be now a stronger attraction for Tommy because we've already lost Timmy. Okay? So this is why mathematically you can find a Ka value for HSO4, but you can't find one for H2SO4. So what that means is that there is a mathematical value that you can determine for this one, but you can't find for the first one. Okay? Does that make sense? So this is why, this is why I'm going to make you memorize the strong acid. So that way we avoid that awkward situation. You go, hey, Gorkamp, what's the Ka of hydrochloric acid? And then I just have to go. Okay? So if you know what the strong acids are, you avoid this look from me. Really? Okay? Then I have to get sarcasm, and I hate it when that happens. Okay, so here's what I want you to get out of this. Number one, this is going to be all about the ice chart, or the rice chart. So when I ask you to do a rice chart, listen to me, Will Stanley. You don't have to write out the water. You can just go HA yielding hydroniums plus your anions. Okay? If it is a weak acid, let's say that starts out at 0.1 molar, you assume that those start off at 0, you go minus X, plus X, that becomes X, this becomes 0.100 minus X. Unless I specifically tell you to worry about the subtraction of that X, don't worry about it. Okay? Don't worry about it. So then you can just go, oh, Ka equals, in this case, X times X divided by 0.1. Now, there is going to be one problem. It's going to be the last problem on the assignment. I'll tell you straight up, it's going to be the last problem on the assignment, where the subtraction of X is important. Okay? And I tell you that. If that's the case, then you have to work this as a quadratic. Okay? There's only going to be one where you have to work it as a quadratic. Don't you like, oh man, I got to do like 5 problems. No, you only have to do one. It's the last problem. But if you look at this, so this is going to be Ka is going to equal X squared over 0.100 minus X. So this is what's known as the 5% rule. So if your percentage of ionization is 5% or less, basically what we're saying is the subtraction of that X doesn't matter. It's so small, it's not going to impact the value of equilibrium. Okay? But if it's like 11% and you're going to have a problem, it's going to be out of the book. You're going to see a problem where it's an 11% ionization. That's so big that you do have to take that into account. Okay? So I will tell you the ones that you have to worry about it. Okay? But here's kind of the cut deal. If it's 5% or less, don't worry about the subtraction of the X. If it's 5% or more, then it becomes relevant. Okay? So let me hand out the assignment. So stop that for a second.